Find the distance between the point Q1, 2, 3 and the line given in symmetric form. X minus 2 over 3 is equal to 1 minus y over 4, which is equal to z over 2. To find the distance between a point and a line, that would be this perpendicular distance here. We're going to take a point on the line, P, create the vector PQ, put the direction vector for the line here, and then if we project the vector PQ onto the direction vector V, if we make that projection, that will be this vector here, and then the distance will be the magnitude of the difference between PQ and the projection. Let's go through the details. So we need this point P and on the line and direction vector V, so let's take the symmetric form and transform that into the vector form. So in the symmetric form, each of these fractions are equal, so we can say they're equal to some parameter t, and we'll use that as our parameter in the parametric form. So x minus 2 over 3 is equal to t, means that x is equal to 2 plus 3t. And 1 minus y over 4 is equal to t, means that 1 minus y is equal to 4t. And so y is equal to 1 minus 4t. And z over 2 is equal to t is simply z equals 2t. And then we can put this in the vector form. xyz equals the point 2, 1, 0 in vector form plus t times direction vector 3, negative 4, 2. Okay, so there's our point P, which will be 2, 1, 0, and our direction vector V, which is 3, negative 4, 2. So now we need the vector from the point P to the point Q. So the vector from P to Q, we take the coordinates of Q and subtract from those the coordinates of P. So 1 minus 2 is, so the vector form, negative 1, 2 minus 1 is 1, 3 minus 0 is 3. So this is the vector from P to Q. Now we want to calculate the projection vector of this vector PQ onto the direction vector of the line V. And the formula for the projection vector is it's a multiple of V. In the picture it looks like it's a little bit shorter than V, but we really don't know how long V is. But anyway, it's some multiple of V, and that multiple is the vector PQ dot V divided by V dot V. So PQ dot V, PQ is here, V is here. So we need to do the dot product of these two vectors. That'll be in the numerator. And then we'll have times V. So PQ dot V is negative 3 plus, so negative 4, and then 3 times 2 is plus 6, divided by V dot V, which is 3 squared plus 4 squared, well, negative 4 squared technically, but that's the same as 4 squared, and 2 squared. So the numerator of our fraction here is negative 1, and the denominator is 9 plus 16 plus 4, that's 29. And then 3, negative 4, 2. So that's our projection vector. Now if we look at this picture, we can see that, let's call this vector here from this point to Q, let's call that vector N for normal vector perpendicular to the line. Then the projection vector plus the normal vector, if we add those two, then that will give us the vector PQ. So N is PQ minus the projection vector. And the answer to the problem is the magnitude of that. N, the magnitude of N. So PQ, which is, so N is PQ minus the projection vector, projection of PQ onto the direction vector V, which is negative 1, 1, 3 minus, that's a negative, so plus 1 over 29 times the vector 3, negative 4, 2. To add these, we want to maybe factor a 29 out of here, so this is 1 over 29 times negative 29, 29, and 3 times 29 is 87. And then 1 over 29, 3, negative 4, 2. So we have 1 over 29 times the sum of these two vectors. Negative 29 plus 3 is negative 26. 29 minus 4 is 25. And 87 plus 2 is 89. So that's our normal vector N, and the distance is the magnitude of N. The distance is the magnitude of the vector N, which is 1 over 29 times the square root of 26 squared plus 25 squared plus 89 squared. So we have to square these numbers, add them up, divide by 29. The arithmetic on this is 9,222. And this one does not have any perfect squares in it. That number happens to be 2 times 3 times 29 times 53. So no perfect squares. That radical does not simplify in any way. So this is the exact distance between the lines, the point and the line.